Hi, I'm Mrs. Stevenson. Torque. A solid steel wheel has a mass of 15 kilograms and a diameter of 0.44 meters. It starts at rest. You want to make it rotate at 8 revolutions per second in 15 seconds. A. What torque must be applied to the wheel? And B. If you apply the torque by wrapping a strap around the outside of the wheel, how much force must be exerted on the strap? This problem deals with torque, which is when a force is applied over a certain distance and torques cause rotation. A good example of torque would be every time you open a door. You apply a force on the door handle, which causes the door to rotate or open. So in order to get the wheel to spin at 8 revolutions in 15 seconds, counterclockwise, the torque must be applied counterclockwise, and the force must be applied to the left. In order to start this problem, we need to list our knowns, which in this case we know our mass is 15 kilograms. Our radius, which if you remember a radius is 1/2 of a diameter, and in this case our diameter was 0.44 meters, so we have 1/2 times 0.44 meters, so our radius is 0.22 meters, so we have our radius. Our initial angular velocity, or omega I, is 0.0 radians per second. Now, our final angular velocity is given to us in revolutions per second. It is 8.0 revolutions per second. But later on in the problem, we're going to have to compare these two. So we need to make sure that we have the same unit. And it's pretty straightforward to change a revolution into radians. So if we have 8 revolutions, and I want to change those to radians, I'm going to set up my conversion, and I know that 1 revolution is equal to 2 pi radians. When I have a revolution on the top and a revolution on the bottom, those cancel, and I just do what's left over. So I do 8 times 2 pi radians divided by 1, and you end up with 16 pi radians, and that was for every second. So we're going to use our final angular velocity as 16 pi radians per second in this problem. Scroll down so we can list our unknowns. We next have to record our unknowns. And in this problem, they're asking us to solve for the torque and the force. But in order to do that, we are going to have to solve for the angular acceleration, which is represented by alpha, the moment of inertia, which is represented by a capital I, tau is the symbol that's used for torque, and then, of course, F is the symbol for force. The equation for torque involves, the torque is equal to the moment of inertia times the angular acceleration. And we also know that the torque is equal to the force on an object times the radius of, or the lever arm of that object. And to help us solve for each of these, we're going to use this equation to help us solve for the force, because it has the force component. We're going to use this equation to help us solve for the torque. So we have to first start with solving for our angular acceleration and our moment of inertia. So let's scroll down and give us a little more room. To figure out our angular acceleration, or alpha, we have our change in angular velocity over our change in time. Now this symbol is delta, and that stands for the change in, which can be written as the final angular velocity minus the initial angular velocity over the change in time, meaning from the start to the stop. From our known section, we learned that our final angular velocity was 16 pi radians per second, and our initial angular velocity was 0 radians per second, and our change in time was 15 seconds. This gives us an angular acceleration of 3.4 radians per second squared, because we have seconds on the top, seconds on the bottom, so don't forget your seconds squared. We're going to save this value to plug back into our torque expression in a moment. We next need to figure out our moment of inertia, which is symbolized by I. For a disk, the expression for the moment of inertia is 1/2 mr squared, the mass being the mass of the disk and the r being the radius, which are both given to us in the problem. So we can solve for our moment of inertia. We have our 1/2. The mass of the disk was 15 kilograms, and the radius we determined was 0.22 meters. Don't forget to square it. So we find that our moment of inertia was 0.36 kilograms meters squared. Now that we have our angular acceleration and our moment of inertia, we can solve for the torque involved in this problem. So remember that the torque is equal to the moment of inertia times the angular acceleration. So our torque is going to be, our moment of inertia was 0.36 kilograms meters squared times our angular acceleration, which was 3.4 radians per second squared. So we get a torque value of 1.2. Now our units, we have to look here. We have kilograms, meters squared per second squared. And another way that you can write a torque unit would be as 1.2 Newton meters, because 1 Newton is a kilogram meter per second squared. And you can see we have a kilogram, there's our second squared, and if we just take one of those meters, we can substitute in the Newton. That's where they get the Newton meter. So we've solved for the torque in the problem. Next we have to solve for the force in our problem. We are going to go back and use our torque expression, which says the torque is equal to the force times the radius. We need to rearrange this because we're looking for force. We want to get that by itself. So I'm going to divide both sides by r. So my force expression is the torque divided by the radius. We just figured out that our torque was 1.2 Newton meters, and that our radius from before we know was 0.22 meters. Our meters cancel, and we end up with a final answer of 5.5 newtons, and a newton is a force unit, so that matches with what we were solving for.